Okay, now that the neighbor's lawnmower serenade seems to have ended, at least for now, we'll try getting into part B. Um, we're talking about temperature, and we were just establishing what absolute zero is. And we now just need to say a word about Fahrenheit. This is the English system temperature system, of course. Everybody's probably already familiar with that. Fahrenheit was set up fairly logically, but the problem is that the reference temperatures were set on two different things, which made it kind of difficult to understand, and basically it made it so that you had weird relationships between the numbers. It was originally set up so that 0 degrees Fahrenheit was the freezing point of concentrated salt water, like basically the saltiest seawater. And 96 was the human body temperature. They were a little off on that, of course. We now know that the average human body temperature is actually 98.6, but they weren't too far off. So using water as a reference, the freezing point of water in Fahrenheit is, of course, 32 degrees Fahrenheit. Sorry. And the boiling point of water is 212 Fahrenheit. Note, for future reference, that the difference between those two temperatures is 180 degrees. Okay, so also in Fahrenheit, room temperature would be considered to be around 70, and body temperature average is 98.6. And in Celsius, which is the metric temperature measuring system that's used outside chemistry and physics, this is, we can make some comparisons with Fahrenheit and also with Kelvins. As I mentioned a few moments ago, Celsius is also known as centigrade, literally because there are 100 degrees between the freezing point and boiling point of water. In fact, water is how the Celsius temperature scale was set up. It makes more sense, at least to me, because both of their reference points were based on the same thing, the same substance, water, whereas in Fahrenheit, one of them was based on salt water, which can vary in composition from one place to another anyway. So a certain concentration of salt water versus human body temperature, which were off a couple degrees anyway. But in Celsius, they based the system entirely on water. For pure water, the freezing point was set as 0 degrees Celsius, and the boiling point was set at 100 degrees Celsius. And that's actually true. The freezing point of water, if it's pure water, is 0 Celsius, and the boiling point of water, if it's pure water, and assuming that you're at sea level, is 100 degrees Celsius. Sorry, I say at sea level because atmospheric pressure varies with altitude, and atmospheric pressure can actually have an effect on boiling point. So the boiling point can actually change quite a bit if you go up into the mountains. Anyway, the difference here is 100 degrees on the Celsius scale. We'll see the significance of that in a moment. In Celsius, room temperature would be about 21. And human body temperature is 37 degrees. Okay, and in order to convert between the two, there are two things that have to be taken into consideration. One of them is that the fact that the two temperature measuring systems have different 0 points. And because, as we've already seen, 0 Celsius is 32 degrees Fahrenheit. So that's a different starting point when you're making measurements in two systems. And also different size of each degree. Degrees Celsius are quite a bit bigger than each degree Fahrenheit, so you have to compensate for that. The formula, if you want the temperature in Celsius, is to take the temperature in Fahrenheit, subtract 32, and divide by 1.8. The 32 is how you compensate for the different 0 points, because, of course, Celsius is 32 Fahrenheit. The 1.8 is how you compensate for the different size of each degree. And this is where we come back to the differences. Notice that the difference between the freezing point and the boiling point of water in Fahrenheit is 180 degrees. But in Celsius, it's only 100 degrees. And yet these are the same 2 points. They're actually the same temperatures. They're just represented differently because you've got two different measuring scales. So the difference between the freezing point and boiling point of water is 180 in Fahrenheit and only 100 in Celsius. Well, if you want to compare the size of individual degrees, you can just take the difference in Fahrenheit divided by the difference in Celsius. So 180 divided by 100 is 1.8. And that's where that comes from. Each degree Celsius is equivalent to 1.8 degrees Celsius. Sorry, did I say that correctly? Each degree Celsius is equivalent to 1.8 degrees Fahrenheit. And there you go. So each degree Celsius is almost 2 degrees Fahrenheit. I think this causes a little confusion in some situations, like, for instance, when scientists are talking about climate change and they say, oh, we're trying our best to hold a temperature change down to, 4 degrees Celsius. Well, a lot of Americans hear that 4 degrees and they think 4 degrees isn't such a big deal, but it's 4 degrees Celsius. A temperature change of 4 degrees Celsius is about 7 degrees Fahrenheit. So that's actually quite a difference. Oh, sorry. If you want to go to Fahrenheit, it's 1.8 times the temperature in Celsius plus 32, which is essentially what you get if you take this equation and rearrange it to solve for TF. You get this. And so you only have to multiply the 1.8 by the temperature in Celsius, not the entire thing, and then you add 32 to compensate for the 0 points. Sorry, some examples, just a couple examples of converting. Okay, that's it, I swear. Between Celsius and Fahrenheit. The record for the hottest shade temperature ever recorded on Earth was, I think it was in 1922 in the Libyan desert. It was 136 degrees Fahrenheit. Pretty warm. Well, what is that in Celsius? So what you need to do is take the temperature in Fahrenheit, subtract 32, and divide by 1.8. So if the temperature in Fahrenheit is 136, we subtract 32, divide by 1.8. 136 minus 32 is 104. Divided by 1.8. and it's 57.8 degrees Celsius. Doesn't seem so bad in Celsius. Seems kind of chilly, in fact, but yeah, that's the difference in the 0 points there and the difference in the size of each degree. 57.8 Celsius is actually brutally hot. And then we might wonder, what would that be in kelvins? Well, if you want to take a temperature in Fahrenheit and change it to Kelvin, it is actually a two-step process. First, you have to do what we did here and change it to Celsius. Then you can go from Celsius to kelvins. And if you remember from the last lecture, temperature in Kelvin is temperature in Celsius plus 273. I'm leaving off the 0.15 because for most purposes, we don't need it to be that accurate. So this is going to be 57.8 plus 273. And that brings us to 331 kelvins, or 330.8 actually, but because of significant figures, I cut it down to 331. Okay, so that sounds even hotter in kelvins. Going the other way, if you remember back a few months ago when they had those huge wildfires in Australia, one of the reasons that those fires were able to get so badly out of control is that they were having a really bad heat wave. And the hotter the temperatures are, the more moisture evaporates from everything. So everything is drier the hotter it is, and burns more easily when it's dry. And during that heat wave, and of course the summer in Australia would be like November and December, so it was winter here, but they were having temperatures hovering around 50 degrees Celsius, which is kind of a real landmark because that, in Celsius anyway, because that is really hot. But Americans hearing 50 degrees Celsius probably think that doesn't sound so hot. So let's convert that to Fahrenheit and see what it's really like. So if we want temperature in Fahrenheit, it's 1.8 times the temperature in Celsius plus 32. Okay, so if we take 1.8 times 50 and add 32. That's 90. 1.8 times 50 is 90 plus 32. Uh-oh, this is looking pretty ugly. And in Fahrenheit, that's 122 degrees. So that's pretty hot. So this is basically how you do the conversions between Celsius and Fahrenheit. And before we go on, I thought I'd just write down a little table here to show you a comparison between temperatures. The book has a chart like this on, see if I can find it, page 15. So you can see there, it's this chart here, figure 112. It doesn't have as many temperatures on it as what I'm going to show, so that's why I'm doing this separately from what's in the book. So we can look at temperatures like absolute zero, freezing point of water, room temperature. I'm going up from the lowest temperatures up. And then the human body temperature and the boiling point of water. And we're going to look at those temperatures in degrees Fahrenheit. R, which stands for the absolute temperature scale associated with Fahrenheit. And we can look at them in Celsius and kelvins, just for comparison. R stands for Rankins, and that is the absolute temperature scale based on Fahrenheit. And so the temperature in Rankine is the temperature in Fahrenheit plus 459. And the temperature in Fahrenheit is the temperature in Rankine minus 459. That's really just for reference. You don't really have to know this because, like I said, Fahrenheit and Rankine are really only used by a few older engineers nowadays. So we won't really be concerned, but I thought I'd throw it in just for comparison. So absolute zero is defined as by the absolute temperature scales. So Rankine and Kelvin would both be 0 for absolute zero, but Fahrenheit would be 0 minus 459, which is negative 459, and Celsius would be Kelvin's minus 273. So it's negative 273 on the Celsius scale. The freezing point of water is 32 in Fahrenheit and 0 in Celsius. Well, 32 in Fahrenheit, when you add 459 to it, you get 491 on the Rankine scale. And when you take 0 and add 273 to it, you get 273 for the freezing point of water in Kelvin. Room temperature in Fahrenheit would be about 70. 70 plus 459 would be 529. I'm putting the squiggle in front, meaning these are approximate numbers for room temperature because opinions can vary on what room temperature should be. You probably know that if you visit your grandparents very often. And let's see, temperature scale on Celsius, room temperature is about 21. And on the Kelvin scale, it would be about 294. The human body temperature is, of course, 98.6 on the Fahrenheit scale. And we already mentioned it's 37 Celsius. 98.6 plus 459 would be 557.6. And when you take 37 plus 273, you get 310. And for the boiling point of water, we know that in Fahrenheit, it's 212. And in Celsius, it's 100. 212 plus 459 would be 671. And 100 plus 273 for Kelvins would be 373. And this array of temperatures here could actually be useful going forward when you're working on temperature conversions for like homework and just practice. It's not very often that they'll give you one of these temperatures to convert, but they might very often give you a temperature that's close to one of these. So if they give you a temperature of, say, 25 degrees Celsius and they want you to know what it is in Fahrenheit, well, you can look here. 25 is a little bit above 21. So your answer in Fahrenheit should be a little bit above 70. And that won't give you the exact number, but it will allow you to check what you do get, because if you get 185 for your temperature in Fahrenheit, then obviously you did something wrong because it should be a little over 70. And 185 is a lot over 70. So yeah, this can be quite useful for future use. Okay, so anytime we're going to be talking about the metric system, we have to talk about the metric prefixes. In the metric system, that's how you change the magnitude of a type of measurement. And the prefix is just a little extension that goes on the front of the name of the unit. And they're also sometimes called multipliers because the prefix represents a factor by which you multiply the unit. So a common one is kilo. Kilo means 1,000. So whenever you see kilo in front of a unit, you know that that unit has been multiplied by 1,000. So 1 kilogram is 1,000 grams. This is as opposed to in the English system, where you have to use different units with completely different names. So in the metric system, if you've got the base unit of length as the meter, if you want to measure something that's small, you can always change to centimeters. Centi is 1/100th. So a centimeter would be 1/100th of a meter. And that allows you to measure small things and get a convenient number out. Whereas in the English system, you've got sort of the base unit of length as feet, but if you want to measure something smaller, you're going to have to use, say, inches. And inches, it's a totally different name, and it's not related to the sort of the bigger unit by any convenient factor. Notice the centimeters is 1/100th or 0.01. That is a factor of 10. The relationship between inches and feet is there are 12 inches in a foot. And while that's easy to remember, because we've all, well, most of us anyway, have grown up with using that system, the problem is that it's not easy to manipulate those numbers in your head like it is with the metric system. At least once you get used to it in the metric system, it's easy because you can always convert from one unit to another just by moving the decimal point. And you just have to know how many spaces to move the decimal point. And when converting from inches to feet, you have to multiply by 12, and that's hard to do in your head. Or, sorry, inches to feet would be, dividing by 12. But anyway, that's hard to do in your head. So the metric units, so as I said, the metric units are related by factors of 10. And adding a prefix is the same as multiplying the unit by that factor. So for example, as I mentioned before, the prefix centi means 1/100th of a unit. 1/100th can also be written as 0.01. Or to emphasize that it really is a factor of 10, 0.01 is actually the same as 10 to the minus 2 power. So that is so 1 centimeter would be equal to 0.01 meters. 2 centimeters would be equal to 2 times 0.01 meters, which is 0.02 meters, and so on. Kilo is 1,000 of something, and that's equivalent to 10 to the third power. 10 times 10 times 10 is 1,000. So 1 kilometer would be equivalent to 1,000 meters. And 2 kilometers would be equal to 2 times 1,000 meters, or 2,000 meters. And so on and so forth. The reason that we use these prefixes is so that we can measure things that are very small or very large and still get a convenient number for the measurement. And so it makes it possible to measure small things with a reasonable number attached. Okay, there is a table on page, what is it, 18, I believe? Yeah, 17, that shows the metric prefixes and the factors they represent. And the you'll notice, if as good on the list, that each prefix represents a multiplier that you multiply each unit by. They go all the way from exa at the top, which is 10 to the 18th power times whatever unit it's attached to, all the way down to etto, which is 10 to the minus 18th power of whatever unit it's attached to. I think in practice, we probably don't really need to memorize all of these, but you should be familiar at least with the prefixes from giga on down to pico. Definitely memorize those. The symbols for the prefixes are over here in the second column. And if you want to abbreviate the unit, what you do is you just put this symbol before the symbol for the base unit. So if you're measuring kilometers, you would take the K for kilo and follow it up with the lowercase m for meters. So the abbreviation for kilometers is just km, both smaller case, lowercase. And the multiplier just gives you the number by which you multiply the unit when you're using that prefix. And way over on the end, that is just showing you that these numbers are factors of 10. For some of the bigger ones and smaller ones, using the exponential version of the a number is probably more convenient. Otherwise, you're going to have to sit there counting zeros before you write it down or before you enter it into your calculator. And that can be tedious, and it's easy to miscount too. So be careful of that. Let me actually just also draw a line through here. Because this pencil line I just drew through here, under kilo but above deci, that represents the base unit. Base unit would be 1 of a unit. So like meters would come between kilo and deci. So that is unit with no prefix would come where this line is. So that represents 1. So all of the prefixes above this line represent values that are greater than 1. There are actually prefixes for every factor of 10. So there is a prefix that means 10 of a unit, like 10 meters, and there's one that means 100 of a unit also, but they're not very commonly used. So a lot of these factors have been left out. And then for all of the numbers below the pencil line are less than 1. And notice the numbers that are less than 1 all have negative exponents, whereas the numbers that are greater than 1 all have positive exponents. And because that's what powers in an exponent, or that's what positive or negative exponents mean. Positive exponent means it's greater than 1. Negative exponent means it's less than 1. So you can look at those and hopefully get used to them working some practice problems. Okay. So the use of a prefix just multiplies the base unit by a factor of 10. That's why why the prefixes are also called multipliers. When I say base unit, remember, I mean a unit without a prefix. So a unit without a prefix would be like meters or grams, or something like that, or say liters. Yeah. Okay, so those would be base units. Okay, so looking at the prefixes, we could look at, say, micro. The symbol for micro looks like a U with a tail on the front of it. It's actually the Greek letter mu, pronounced, like a cow says, mu. It's the Greek letter, it's the Greek equivalent of an M. The thing is that we've used so many M's for abbreviations in the metric system so far that we ran out of M's. Lowercase m means meter, and uppercase M means mega as a prefix. So what are you going to do now? You got to find something else to be an M. Well, they noticed that the lowercase mu in Greek looks different, so they decided to use that. And so there you go. You can actually just draw it as a U with a tail on the front of it. You can kind of see how it developed into an M just as a tangent here. If you write it kind of like that, kind of looks like an M, doesn't it? And that's exactly how it eventually developed into what we know as the M today. But anyway, that's enough of that. So micro means 1/1,000,000th. Of a unit. Or 0.000001 of a unit. Or 10 to the minus 6 of a unit. One, two, three, four, five, 1. So if you have 35 micrometers, or micrometers as it's sometimes called, that means 35 times 0.000001 meters, or 0.000035 meters, or 35 times 10 to the minus 6 meters. That's not proper scientific notation, though. For proper scientific notation, it has to be a number between 1 and 10 times 10 raised to some whole number power. So we notice that this is 35. If you move the decimal point one place to the left, you get 3.5. That is between 1 and 10. So that's what you have to do. Notice that in moving the decimal point one space to the left, we made this part, the first part of the number, smaller. So we have to make the exponent bigger to compensate. Because we don't want to change the value of this number, we're just trying to change the way we represent it. So if one part of the number gets smaller, another part has to get bigger in order to compensate. Now, this is a negative exponent, so you have to keep in mind that when negative 6 gets bigger by 1, it goes to negative 5. And 3.5 times 10 to the minus 5 would be the result. Okay. And so an example of choosing a prefix because it gives you a reasonable number rather than just using the standard unit for something is where you notice that the wavelength of light from sodium vapor streetlights, and those are the yellow ones, is 5.89 times 10 to the minus 7 meters. Now, 5.89 times 10 to the minus 7 is kind of an inconvenient number to have to deal with because it's in scientific notation, and we'd really prefer to deal with, regular numbers if we possibly can. Well, that's why we have metric prefixes. If you attach nano to the word meter, you get a factor of 10 to the minus 9 multiplied by the meters, and in that case, it's actually 589 nanometers. 589 is a much more convenient number to deal with than 5.89 times 10 to the minus 7. And to show you how we do that, I said this is 589. I mentioned that nano means 10 to the minus 9. Okay. So the 10 to the minus 9 part is what nano means. And if you change this to proper scientific notation, notice 589 is not between 1 and 10. You have to move the decimal point 2 places to the left, and you get 5.89 times 10. Now, moving the decimal point 2 places to the left made 589 smaller, so you have to make the exponent bigger by 2 because you moved the decimal point 2 places, and it's a negative number, so be careful. When negative 7 gets bigger by 2, it becomes negative 5. Wait a minute, 5.89, sorry, negative 9 gets bigger by 2, it becomes negative 7. Sorry, that's where we started out. I was looking up here instead of here. So negative 9 gets bigger by 2, it becomes negative 7, which is what we started out with. So those two numbers are really the same thing. It's just that this one is much easier to deal with. Okay, I'm a little bit over again, so I'm going to stop there for part B, and I'll see you in part C in just a moment.